Okay, so it's my pleasure to welcome Andrew Snowden. He's going to talk today about some recent work on multilinear forms.
Yeah, thank you very much for having me. The different parts of this talk will be going to work with different people, but let me just say some names at the beginning. So there's Arthur Berry and Alessandra Danelon and Nate. All right, so let me start with something very basics. Let's consider quadratic spaces, by which I mean a vector space. And this talk, everything will be over the complex numbers. So there's going to be a complex vector space with a symmetric bilinear form. Okay. And here are some properties of these things, properties in the finite dimensional case. So first of all, you can classify these things. If you have a quadratic space, you can look at the null space of the quadratic form, and you can look at its dimension. That's obviously an invariant. I'll call that the nullity. Dimension of null space. And then you have the rank. And the rank is just the codimension of the null space. And so you get these two numbers, they sum up to the dimension of the space, and this is a complete, this pair of numbers is a complete invariant. Okay. If you look at a random quadratic space, like you randomly pick the form, and I don't want to try to say what that means exactly, but almost certainly you'll avoid having any null space whatsoever. A randomly chosen form will have full rank. So a random form has nullity 0. And this no null space means the form is what's called non-degenerate. And in particular, if you pick two random forms in the same dimension, they're going to be isomorphic since they have the same invariance. So two random forms, same dimension, or isomorphic. So really, there's kind of like a best form in each dimension, which is the non-degenerate one, and the random one will be in that isomorphism class. And then finally, the non-degenerate ones, these best ones have some very nice properties. So one is that you have this theorem of Witt's theorem, which says that if V is non-degenerate, well, the kind of simplest statement that you can make is that you can look at the automorphism group of V, which is the orthogonal group, and that doesn't act transitively because it preserves the norm, but the norm is the only invariant. If you have two non-zero vectors with the same norm, the group can move one vector to the other. So you get this highly, not transitive, but almost transitive action. And there's an even better version of that statement. It's not just that if you have two vectors with the same norm, you can move one to the other. If you have two finite lists of vectors, and all the inner products of them are the same, then you can move one list to the other list. And kind of a more abstract way of saying that is that if you have any other quadratic space, so if V is non-degenerate, and we have two embeddings into V. So here W is some other quadratic space. So if you want to be less abstract and you pick a basis for W, that's giving you these two lists of vectors that I was talking about. Then there exists some automorphism of V that moves one embedding to the other, such that I is equal to G opposed to J. Okay, so all this is basically linear algebra. The kind of question I want to think about today is, if we change quadratic space to like cubic space, what happens? So what about higher degree forms? You say that, well, obviously that everything breaks. So the kind of lots of the above break. Okay, so let me say something concrete. So if we look at, so if you're thinking about quadratic forms in an n-dimensional vector space, you can think of them as an n by n symmetric matrices. And what it means for two of them to be isomorphic is that you can move one symmetric matrix to the other using an invertible matrix, right? And the group GL is acting by GEG transpose on these symmetric matrices. So the kind of same thing here. If we're thinking about cubic forms, well, now you have to think about sim3 Cn, maybe a dual. So this is like the space of symmetric trilinear forms on Cn. And GLN acts here. And to say that two of these things give you isomorphic cubic spaces means that they're in the same orbit, right? So understanding isomorphism classes is the same as understanding orbits. But now what happens is that the dimension of this ambient space, the dimension of sim3, is approximately 1/6 n cubed. And the dimension of GLN is n squared. So that means when you do the orbit space, you subtract dimensions, and it's still going to be about n cubed. But certainly, if you choose two things at random, they're not going to be isomorphic, and there's no best isomorphism class. So those kinds of things break down. And moreover, it's true that if you pick like a random form, so a random form in this class will have finite isomorphism, or has finite, automorphism. So like if you have a smooth cubic hypersurface outside of dimension, some small dimensions, the automorphism group is finite. And so of course nothing like Witt's theorem is going to hold, because if you think about two vectors on the hypersurface, they have to both have norm 0, but you can only have finite orbits, so you're not going to be able to move everything there. All right, so this is all looks very bad. And the point of this talk, though, is that if we go to infinite dimensions, we can kind of rescue a lot of good stuff. Things are nicer in infinite dimensions. Now I'm going to start playing some of this new stuff. And so let me start with some language. So let's fix a tuple of positive integers. And it's not mixed integers. This sigma, we're going to call this the like signature that we're working with. And so we're going to define what we call a sigma space. So this is supposed to be a generalization of the idea of a quadratic space. So a sigma space is a vector space V with symmetric multilinear forms. Let's call them omega 1 up to omega r, where omega I has like arity di. Arity just means how many arguments it takes, right? So when di is 2, you have bilinear forms of d is 2. Okay, so let me just make this kind of concrete. So if sigma is just, if we just have one number and it's 2, then we're getting quadratic spaces. If sigma just has one number and it's 3, then we're getting what I would call cubic spaces. These are spaces with one symmetric trilinear form. But we can also consider like a case when sigma is 2 comma 2. And then these would be a vector space with 2 symmetric bilinear forms. And I call these biquadratic spaces. And these two forms can be completely unrelated, totally free to choose them, right? Okay, and then there's a notion of embedding. So an embedding of sigma spaces, let's say W to B, So these are both sigma spaces, and this should just be is an injective linear map, such that the forms on V pull back to the forms on W. And now we can, in this language, we can kind of state what Witt's theorem means. So Witt's theorem, you can think of that, right? Did I erase it? Yeah. So Witt's theorem, you can think of that as like a property of this non-degenerate space V. It says something about when you have embeddings into V, something happens, and that makes sense in this context. We say that a sigma space V is called homogeneous if it satisfies the conclusion of Witt's theorem. So if, well, okay, sorry, I have to be a little more careful here. So if for all embeddings, all really pairs of embeddings, ij of some sigma space W into V, but the reason I have to be more careful now is that this is only going to be for finite dimensional W. Where W is a finite dimensional sigma space. There exists some automorphism of V that ij. So we are going to be interested in infinite dimensional sigma spaces, of course, but this definition of homogeneous for finite dimension. And then finally, one more definition. So we say that a sigma space V is called universal if all finite dimensional sigma spaces embed into it. So that's a bunch of definitions. So let me tell you how it's different. So this theorem is was one that Nate and I proved together, and I think he talked about it in this seminar maybe 2 years ago or so. So maybe some of you will recognize this. Yeah. All right. So the statement is that there exists a universal homogeneous sigma space of countable dimension, countable infinite dimension, and any two of these are isomorphic. And I think that's really amazing because it's kind of saying like all the good things that happen in the Witt's theorem case hold true here, even though we have higher degree forms. You never can see symmetries like this. It's very cool. So some remarks. So first of all, if we look at the automorphism group, we call the space V. So if we look at the automorphism group of V, this is really large. So like in the case when sigma is just like 2, this V is going to be an infinite dimensional quadratic space with no null space full rank. And this is going to be the infinite orthogonal, okay, which is like an infinite dimensional equilibrium. And in general, these G's, they sort of look like the infinite orthogonal. I mean, they're of course a little bit smaller, but they're still like infinite dimensional equilibriums. And they just don't have any finite dimensional counterparts. So this is really constructing all these new infinite dimensional equilibriums, which I think is really, really cool. So one way to see that it's huge is that, well, let's just say that, let's consider the case when sigma is D. So we have just a single form. We have one form omega. And we can consider like the norm 0 hypersurface defined by this. So we have the omega equals 0 locus inside of PV. And G is going to act transitively in this. That's a consequence of this homogeneity. And so like in finite dimensions, you know, I said that a degree D hypersurface that's very small. Here you get this big leap. Okay, that's one thing I wanted to say. What else did I want to say? Oh yeah, so I told you what V is when sigma is 2. That's the easy case. There's also a nice answer we know when sigma is 2 common in the quadratic case. So here we have 2 symmetric bilinear forms on V. And you can really think about a symmetric bilinear form as a symmetric matrix, even in infinite dimensions. You just pick a basis for your space and you just record the pairings. And that's a symmetric matrix. And there's no restriction to it. It doesn't have to be both lines or column lines. You just have this structure just corresponds to two symmetric matrices. Either two infinite by infinite symmetric matrices. So that's what a 2-2 space is. And now some of these, for some choice of A and B, you'll get this space and some you won't. So there's some condition which gives you this universal homogeneous case, and that's characterized in the following way. So this is universal homogeneous if and only if the columns of A and B are linearly independent. And by that I mean, like, you take all the columns of both matrices together, that set of vectors has to be linearly independent. And that kind of starts to show you maybe what's going on here, because if you think about n dimensions, if you have two n by n symmetric matrices, you have two n columns of those two matrices. And there's no way a set of two n vectors can be linearly independent in n dimensions. But if we're working in this infinite dimensional case, the columns of this matrix can have infinitely many non-zero entries. So that's really an element of the dual vector space. And the dual vector space is much larger, right? I mean, it's going to be uncountable dimensions. So you can find, however long of a list of linearly independent things you want, basically. And then finally, let me say that, so this is talking about countable dimension, and this all breaks in uncountable dimension. So everything even breaks just for quadratic space. So in countable dimensions, quadratic spaces work like they do in finite dimensions. You can find orthonormal bases, and that can be uniquely characterized as isomorphism. In uncountable dimensions, you can't find orthonormal bases. So in fact, it's known that there's infinitely many isomorphism classes of non-degenerate quadratic spaces in uncountable dimensions. Yeah, it's uncountable dimensions. I learned this from a book by Herbert Gross in quadratic forms. Okay. So this theorem is like maybe hopefully convinces you that in infinite dimensions some nice things do happen. And this was kind of like, I guess, my starting point in thinking about these sigma spaces. When Nate and I proved this, it made me realize that there might be a nice theory here. So I kept thinking about it. I've been doing more stuff. The reason Nate and I were originally interested in this is that we wanted to construct these groups. We had some potential applications in mind, which it's haven't borne real fruit yet, but it's still an interesting idea.
Still have hopes.
All right, so I think the next thing I'll tell you about is a little more about this universal condition. There's a nice characterization of that I want to say. And one other thing I should mention is, so I define these sigma spaces when you have like this tuple of integers. There's a more general version of this where instead of integers, you can have partitions. And then, like if you, like a symmetric form of degree D is a map from sim D to your base field. If you have a partition, you can put the Schur functor there instead of sim D. And that'll give you things like alternating forms and some mixed behavior between symmetric and alternating. But it's all pretty much the same. Okay, so right, to tell you about universality, I need this idea of what's called the strength of a polynomial. So let's suppose that f is a polynomial in n variables, and it's homogeneous of degree D. So the strength of f is the minimal s, such that you can write f as a sum of s things which are coming from lower degree. I guess to be technically correct, I should say infimum here, because if F is a linear form, there's no expressions like this, and the strength of linear forms is defined to be infinite. Right, so this idea of strength kind of is a measure of complexity, like how complex your polynomial is. The strength, one things are exactly the things that factor. So it's like kind of telling you how many things a smaller degree you need. This terminology was introduced by Danelon and Hoxter. They used this strength in their proof of Stoneman's conjecture, the conjecture in commutative algebra. In fact, this invariant appeared earlier in the paper of Schmidt. So there's a community of people who call this Schmidt ring instead of strength. Schmidt used it in kind of an analytic number theory context. It's been playing this idea of strength or Schmidt break, whatever you want to call it, has been like really kind of a hot topic recently. There's a lot of different things. It's just, yeah, it's a very useful invariant. So we can also make sense of strength for like if you have infinitely many variables. So if we kind of go to the kind of inverse limit of the strength, so you can imagine like some infinite series in the variables, and as long as you have homogeneous things there, you can still talk about strength. So makes sense for infinitely many variables. And in that context, you see a lot more things that have infinite strength. So for example, if you look at the sum of all the squares, cubes or whatever, that'll have infinite strength. So for quadratic forms, strength and rank are almost the same thing. They're off by a factor of 2 or something. So infinite rank and strength is the same. All right, so here's the theorem. This is due to Kazdan and Ziegler. Okay, so let V be a sigma space. And let me write down the name of the forms. So we have omega 1 and omega r are the forms. Then the following are equivalent. Condition 1 is that V is universal. And remember, this means that every finite dimensional sigma space intensity. That's what it means. The other condition is in terms of strength. And well, you want each of these things to have infinite strength, but you want a little more than that. You want that true for linear combinations, as long as it makes sense. So strength is only defined for homogeneous things. So you want to say that if you take any homogeneous linear combination of these, which is not the trivial linear combination where you just take all zeros, that such things have infinite strength. So strength of any non-trivial homogeneous linear combination. Does what?
Doesn't have to be homogeneous.
It doesn't have to be homogeneous?
Meaning that you could have a form of degree 2 in a cubic form and you still look at the.
No, that's what I mean by homogeneous here.
Oh, sorry.
Yeah.
Sorry.
Oh, yeah. Yeah, so like in that case, you just have 1 degree 2, 1 degree 3, or just say that each one separately isn't.
All right.
Yeah. It's actually a really cool theme that happens in all this strength stuff, that like things of different degree tend not to interact. So this is a really useful theorem because, you know, maybe you can sometimes prove things in the universal case, but that's a useful hypothesis to have. And then if you're not universal, you have finite strength, which kind of means you're built out of something simpler. So maybe there's some inductive argument. So Pratt and Ziegler, by the way, were working in the context of like additive combinatorics and this idea of, they call it Schmidt rank in that context, but really important tool for them there. Okay. Yeah, and also, so Kazdan and Ziegler, they kind of never work in infinite dimensions. So if you look at their paper, it's not set in this way. So they work in finite dimensions, and of course, in finite dimensions, any polynomial has finite strength. So the theorem they prove is actually stronger than what I wrote here. It's a quantitative version. And so their theorem says that, let's say that you have your V, and of course, it's not going to be universal, it's finite dimensional. But maybe you're interested in embedding all 2-dimensional sigma spaces into V. then their theorem says that as long as the strength of these things is large compared to 2, that all 2-dimensional space is bed. Okay, so it's just this kind of finite version of this theorem. All right, so what I want to talk about now is kind of, and this theorem, by the way, predates the work that Nate and I did, so they proved that first. And what I want to talk about now is work that came after what Nate and I did, so more results in sigma spaces. So the kinds of things I've been thinking about kind of since Nate and I proved that theorem are trying to classify sigma spaces. And well, it's really hard to classify all sigma spaces up to isomorphism. I think that might be too hard of a problem. It might be kind of unsolvable. But there's 2 weaker versions, which I think have nicer answers. So the first weaker version works with all sigma spaces, but coarsens isomorphism and makes it a weaker equivalence relation. And this is what we call isogeny. So let me tell you about classification up to isogeny. So first of all, what is isogeny? So we say that V and W, these are 2 sigma spaces, are isogynous if each embeds into the other. Okay. So this relationship of V embedding into W is what people would call a quasi-order. It's kind of like a partial order, but if you have V less than W and W less than V, they bend into each other. They're not isomorphic, they're just this isogynous. So if you take the set of isogeny classes, that's actually partially ordered by inclusion. So you get this nice partially ordered set. And I guess the main problem is described as poset. Right? The poset of isogeny classes. And here, I guess, we're just always going to restrict to countable dimensions because there's nothing to say in uncountable dimensions as far as I know. Okay, so let me tell you about some results. So there's this paper by Dick, Reisma, Danelon, I guess the names are out of order, and Egermont, these 4 guys. And actually the main point of their paper was generalizing this theorem to the case when you have partitions in your sigma and they're not just symmetric powers. So that version of the theorem exists. But they proved something about isogeny classes in that paper as well. They showed that this poset always has a unique maximal element. And well, this paper came before the work that Nate and I did. I mean, the stuff that Nate and I did kind of makes this obvious because this universal homogeneous space has this property that everything embeds into it. And so that's well defined up to isomorphism. So the isogeny class of that thing will be this maximal element. There will be potentially other things in that isogeny class besides this one special space, but anyway, that nails it down. And they also showed another result, which I don't know how to prove independently of their proof, which is that a unique minimal class exists as well in certain cases. A unique minimal class exists if all the degrees are the same. Okay, so that suggests that there might be some nice structure to this poset. So these are kind of the first results from this problem. So kind of these results of theirs that you have these maximal minimal classes at least some of the time is kind of what spurred me to think about this isogeny problem more generally, that it might have a nice answer. And I guess like one of the first non-trivial cases is just to think about cubic spaces. And so that's this paper that I wrote with Dick and Danelon and me. So we figured out isogeny classes for cubic spaces. And let me tell you how it works. It's actually a very simple answer. It's really nice. So let's say that we have a cubic form. like on an infinite dimensional space. So let's say on C infinity. So you can think of this as just like a kind of a polynomial in variables x1, x2 up to x infinity, but it can be an infinite sum, so like have the sum of xi and q. So I'm going to define an invariant of the cubic form space, which we call the residual rank. Okay, so if I have a vector, let me say something before the definition. If I have an actual vector in C infinity, I can take the directional derivative of that in this direction. And this will be a quadratic form on C infinity. So if you're actually thinking of f as like a kind of a cubic polynomial, this is like taking derivative. If you want to think of f as a symmetric trilinear form, this is like plugging v into one of the slots, and then you get a bilinear form of the remaining two slots. Okay, so that's what this operation is. So the residual rank of f and we denote this by RRK of f is, all right, so what you do is you take all these derivatives. This forms a vector space because this operation is an additive thing. So the dimension of this vector space is not so interesting, almost certainly going to be infinite. So we do something a little different. What we do is so this is sitting inside of the space of all quadratic forms. And we quotientify the quadratic forms of finite rank. And then we take the dimension of this space. And okay, I wrote this in a slightly misleading way because this is not, this thing doesn't have to contain all forms of quadratic of finite strength. So I really mean like intersect this down with this, and then that's the dimension. So another way to say this is if you want your residual rank to be at least 5, you have to find 5 directional derivatives such that no linear combination of them has finite rank. Okay. So let me do an example or two. So if I take f to be this guy, which is the sum of the variables q, then if I take like the ith derivative of this, this is just xi squared, and that's a finite rank quadratic form. And any vector, anything in C infinity, kind of is sort of like a finite linear combination of xi. So if you take some other vector, you're just going to get some finite sums of things like this, and it's still finite rank. So none of these have infinite rank. This means the residual rank is 0. So yeah, this f has infinite strength. You can say the strength of f is infinity, and the residual rank is 0. Okay, so here's an example where you actually do pick up residual rank. So let's say that, okay, so here I'm working on an infinite dimensional space. I just have like an infinite list of coordinates, and I can sort of call them whatever I want. So it's going to be clearer to have xi's in. So I'm going to take x1 times the sum of yi squared. And then I'm going to add in another part, I equals 2 to infinity of xi cubed. And here you see when I take the x1 derivative, I'm getting an infinite rank form. The x1 derivative is the sum of the yi squareds. That has infinite rank. Every other derivative that doesn't use an x1 has finite rank. So here the residual rank is 1. Strength is still infinity, residual rank is 1. And actually, you see in this case, if we omitted this second term, it would still have residual rank, but now the strength would be finite. So these two invariants are kind of independent of one another. And using kind of the same idea, you can get to infinite residual rank. So we could take f to be like sum from I equals 1 to infinity, and then we have xi. And then with xi, we put a quadratic form of infinite rank, but all the different ones are going to be in different variables. So we do like a sum from j equals 1 to infinity of yij squared. And this will have residual rank. And one other thing to note is that if I have my cubic form on C infinity and I restrict it to a subspace of C infinity, the residual rank can only go down because there's fewer v's that you can look at to look at the quadratic forms. And each of those quadratic forms, you're only looking at the rank of that form on the subspace, so the ranks of those forms can only drop 2. So when you have an embedding, maybe I should write it down. So if V to W is an embedding of cubic spaces, then the residual rank of the V space, let's make it the residual rank of the W space. And in particular, this means that if V and W are isogynous, then they have equal residual rank. Yeah.
Probably to be question, what is the first one of infinite strength?
This one?
Yeah.
Oh, that's not necessarily obvious. But there's not an obvious way to show that it's finite strength, right?
If you don't factorize in the usual like decomposition of the cubic sum of cubics.
I mean, maybe you can like factor out one linear form, but no, you can't even do that. Right? No, sorry, it doesn't matter. But you can get like a geometric series type factorization.
So what was
I mean, like the Fermat cubic is an irreducible hypersurface, right?
Yeah.
Like, so yeah, it's irreducible. No, but yeah, it's infinite string. Okay, so yeah, maybe now you can sort of guess our theorem. So we have the proposed set of, okay, so in our theorem, we actually only work with the universal cubic spaces, so the infinite strength case. So we have the proposed set of universal cubic spaces up to isogeny. And this thing here says that residual rank is a well-defined map on that set. And the residual rank can be 0, 1, 2, 3, up to infinity. And this is an isomorphism process. So Alessandro, that's the Danelon. Alessandro is my current postdoc. So he and I have been thinking about isogeny beyond the cubic case now. And we have a conjecture for how it works in general, actually. And it gets very complicated. I want to say just a little about it. So I wanted to reference these examples a lot. Okay, so the way that we got that residual rank infinity example was we kind of started with, x1 times an infinite strength quadratic form. And then we just kind of made copies of that form and summed it with itself, right? And that gave us one with infinite residual rank. So another thing that we had considered on the board was just if we took x1 cubed and made copies of itself, like x2 cubed, x3 cubed, and summed those together. And that gave us a residual rank 0 thing. And the kind of general idea is if you're in degree D, you can kind of take the things that you know from 1 degree lower and sort of take products of them and then do infinite sums of things that look like that. Okay, so like in the quartic case, you can consider like sums like FI, where FI and GI are infinite strength quadratic forms, and the variables that appear in all these forms are disjoint. So that's like one kind of thing you could do. You could also do the case where FI is linear and GI is a cubic of infinite residual rank. Or anything that you've already seen from the cubic case, like a sum of xi cubes. And so there's this kind of recursive structure where it's like you can take things from lower degree and package them together. And so sort of the things that you see, the kind of combinatorics of it kind of correspond to like trees where the leaves are weighted by your numbers. And so like a tree like 2, 2 is kind of corresponds to this, where it's like you take 2 quadratic forms, kind of the basic pattern, and you sum them up into times. You could also have something like this. And this would mean, well, we put another linear thing here, and then we sum all those things together. Okay. And these things do not classify isogeny classes. So once you go beyond the cubic case, there's continuous families of isogeny classes. So you're not getting like a combinatorial classification, but these are kind of the basic combinatorial objects that appear in the classification. And there's actually, yeah, something that I do want to try to say is that, so, okay, if we go back to this cubic case, we have our space of cubic forms on C infinity, which is this. And on this, the group G on infinity acts, but actually there's a larger thing acting, which is the monoid of infinite by infinite matrices. And if you think about it, what does it mean when you have something here and you act? That's kind of like, this is a map from C infinity to C infinity, and you're pulling back the form, right? So this thing that you get will, at least if you acted by an injective matrix, that would be something that embeds. So this is kind of moving down in the isogeny order. And so for two things to be isogynous, you want like each to be in the orbit of the other under this monoid action. So like classifying isogeny things is like kind of classifying orbits of this monoid. And a coarser problem would be to classify subrepresentations. This is a linear thing with this thing acting linearly. So you can try to classify just subrepresentations. Two isogynous things generate the same subrepresentation. So classifying subrepresentations is an easier problem. And we do that. I mean, this is ongoing work. We haven't finished all the details, but I think we're going to accomplish that. And the subrepresentations are indexed by these kind of basic combinatorial things, these like trees. And what's really cool is that these things are finite length representations, which is really kind of amazing. So actually, this gives you this very interesting category of representations of the infinite monoid, things that appear in subquotients of these kinds of things, and that's closed under tensor products, and it's an abelian category. Everything has finite length. It's a really interesting object. But the symbols correspond to these trees, and it's like if you start with some finite list of objects and then start taking tensor products in summations, you don't get everything. It's not like kind of a finitely generated tensor category. It's an extremely complicated object, and I still don't know. Like one thing I'm interested in is finding out the like right language to describe this. Like it feels like a very basic object in a way. Okay, maybe it's a little bit esoteric, but in some sense it's a very basic object, and I think it should have a nice description. It's just the language of tensor categories alone is not enough. There's more structure this has, and I don't know how to formulate that yet. Okay, so one other direction I want to talk about just in the last few minutes. This was here I was talking about classifying all spaces up to isogeny. Another problem that you can consider is to try to work with just a special class of spaces and determine them up to isomorphism. And the special class of spaces I would consider are ones which are very symmetrical, highly symmetrical spaces. Okay, so let me start just by saying the following. So if V is a sigma space, and we let G be its automorphism, then we can think about V as a representation of G. And that means we get an invariant. We can consider the length of V as a G module. And for these universal homogeneous spaces that Nate and I constructed, I said that they were very symmetrical, that G was huge there. And you can show that they're always irreducible as long as you don't have linear forms, because if you have an invariant linear form, of course, you're putting out some trivial representation. But they always have finite length, and they're typically length 1. So what about other spaces of finite length, right? I mean, finite length does mean that the symmetry group is pretty large. That is kind of saying that you're highly symmetrical in some way. And well, here's a theorem that Alessandro and I have proved. Okay, I'm not actually going to state the full theorem, but we classify all the universal biquadratic spaces of length 2. Okay, and the answer is that there's 7 families. And I mean, some of these families have discrete parameters, some have continuous parameters. I'm not going to say the whole answer, but it's very explicit what it is. And rather than trying to tell you what the actual answer is or anything about the proof, let me kind of tell you like why this should be a tractable problem and like kind of how this relates to some other interesting stuff. So let's say that you had one of these biquadratic spaces. So you have two symmetric bilinear forms. Like what kind of stuff can you do? So you can produce like kind of new spaces of your space by like considering the null space of one form, or the null space of the other form, or the null space of a linear combination. So actually, those are potentially all different spaces. So that's giving you like a P1 parameterizing, P1 parameterizes this family of subspaces that you have. Another thing that you can do is you have your two forms, let's call them omega1 and omega2. You can look inside of V times V, and you can look at the set of pairs XY, such that the X derivative of omega1 is the Y derivative of omega2. And this is kind of like a more general version of what I was just saying, because if you look at like, the things where Y is 0, that's giving you the null space of omega1. Okay? But now if you have something in V times V, you can get a lot more things, because like you can take this space and project it and take things you already know and do intersections and pullbacks and sums, and you're going to get a whole bunch of spaces. And these subspaces are kind of from a model theory point of view, you would say that they're the ones that are definable in this language. Like you have this language of linear algebra, you have vector spaces and sums and scalar multiplications, and you have two forms. And if you think about like the formulas that you can write down in those symbols, that will give you kind of these spaces that I'm talking about. And all these definable spaces are kind of obviously stable under the group G, right? So they all give you sub-representations. So if you're saying length 2, that means that there's very, very few sub-representations, and this huge, tower of definable spaces has to collapse radically, right? And that gives you a lot of leverage. And that's kind of what we use to get our hands on what's going on here. And well, in fact, in these cases, every sub-representation is one of these definable spaces. So there's not any like kind of weird sub-representations that you sort of can't explain. And that's like a very interesting general question. If you have a highly symmetrical space, does it always have that property? And well, as I've defined it here, finite length, that's kind of actually not good enough to mean highly symmetrical once you go past biquadratic spaces. Or it might be good enough for multi-quadratic spaces as well. But once you have cubic spaces and beyond, it's not good enough. And let me just tell you one example that says why. So there's an example that Alessandro and I found. So there exists a 3-4 space, V, such that V is an irreducible representation of G. But if you take the second tensor power of V, this has infinite length as a G module. And this kind of means there's going to be like way too many sub-representations appearing somewhere for any of this stuff to work. It's just too badly behaved. So really the right condition is not finite length. Like that doesn't mean that the space is symmetrical enough. Like you want this, but that's not good enough. You would want all the tensor powers to be finite length as well, but even that I think is not good enough. The right condition is something that Nate and I introduced. We introduced this class of groups called linearly oligomorphic groups. And I mean, I just be very quick. The basic idea of the definition is that if you look at the set of all subspaces of V, D-dimensional subspaces of V, and you look at the orbit space, that should be a finite dimensional topological space. It's the intuition of the definition. And so I sort of suspect that if you look at spaces whose automorphism group is linearly oligomorphic, then this kind of comparison between model theory and sub-representation should work out. And that there might be a nice classification of such spaces that extends what Alessandro and I did. But that all seems very, very hard at the moment. Like I really don't know how to go past what we've done. So I'll stop there.
So back up to this stuff that's at the very top there.
Yes.
So this is when you're talking about specifying things up to isogeny.
Mhm.
And you sort of mentioned that you have these trees showing up as kind of objects in this tensor category of the additional structure. Can you say a little bit more about what sort of additional structure we're seeing here?
Yeah, so I can tell you the basic idea, although I don't know how to make it really work in full generality. But if you think about this space, cubic forms. Okay, so I've written this kind of abstractly, but if you want to be concrete, these are just cubic forms in your x1, x2, et cetera, in your Latin. Any formal linear combination of degree 3. So this space has a topology. It's the inverse limit. And And so if you have a set, you can take its closure. And well, anything that you consider inside of your reasonable thing is probably dense. So that's kind of an uninteresting thing to do. But there's kind of like a different closure that you can do that is much smaller. And you can look at, so if I have I can look at like sums like this. Okay, so what does the topology mean? So this is an additive topology. So for a sum to converge, the things have to go to 0. And going to 0 means that each variable appears only, well, it means that if you want fi to be divisible by xi, basically, like you want things more and more divisible by higher and higher variables as you go on. Okay. So that's like the standard convergence. A different kind of thing that you could ask is that each variable appear only finitely many times. Okay. So like, I'm sort of declaring this to be an allowable thing. But if you like imagine like, you know, x1, x2 plus x1, x3 plus x1, x4, this sum does converge. Each monomial appears once. But I'm saying that this is kind of not the kind of sum I want to consider. Okay. And so like considering these kinds of sums gives you interesting things. Because if you start with just polynomials and you take the kinds of sum I'm allowing, you'll see these kinds of things which have residual rank 0, but you won't ever build a residual rank 1 thing. And so this is the idea. You have this, so we call this pi. So if you have v inside of here, you get this pi of v, which you get by considering these kinds of restricted convergent sums. And so what you can do is you can, you know, whenever you have things in lower degree, you can tensor them together and then take some ends of that or subgroups and then do pi of that. And so these kind of nested pi things is where these kinds of trees are coming from. And so my general idea is that this is like a tensor category that has some sort of completion functor on it. And that should be the kind of universal description of it. But this completion functor is kind of only truly defined on the basic objects. It's not defined on the general objects. And I don't know how to make that work. That's the problem. Yeah. Yeah.
So you think about the structure of these groups?
Right. So that's an easier question. Why I wanted to construct them. So I said that we call these linearly oligomorphic groups, and the reason is that they are linear analogs of groups that appeared earlier called oligomorphic groups. So if you have a permutation group, so if your omega is just some set which is acting by permutations, this is called oligomorphic. If G has finitely many orbits on each Cartesian tile. Okay. And so this is kind of an analogous thing. So it's saying that there's finite dimensions of orbits on each tower. And Nate and I did this work where we took oligomorphic groups and we constructed tensor categories from them, ones that people have never found before, and they're very cool. And it looks like that. So like the basic example of an oligomorphic, by the way, is the infinite symmetric group acting on an infinite delta set. And there's this kind of tensor category that Danelon constructed from that. And if you take GL infinity, the algebraic group, there's also a tensor category corresponding to that. And that's one of these kind of linearly oligomorphics. So we're thinking that, you know, maybe there's an analogous picture over here that extends what we had already done over here. But that's what we haven't been able to do.
So they're
Yeah, I don't have a rigorous definition of that, but that's why.
Do you know if they're like possibly?
No, I don't think so, but I don't know. Yeah. We haven't really studied them in much detail, and I think there's a lot of lead theory there that's very interesting to think about. Like you could ask, are there maximal tori, are there Val groups, are there parabolic subgroups, how you understand all that? It seems like some of that theory should work, but I haven't really thought it through.
Effective invariance there.
Yeah, I mean that does happen because GL infinity like does have these parabolics where the quotient is the Grassmannian. You can certainly like infinite Grassmannian. You can certainly think of that as a projected infinite dimensional variety in a certain sense.
Now let's time this figured out.
Yeah.